Okay, we're going to start with today is we're going to move into the subject area of thyristors. Now, this is a group of electronic components that basically they're all of a similar characteristic, and it's that they operate with the influence of a gate signal. Okay, so they're a little bit different than diodes or transistors. Okay, so the group of thyristors has a few components in it. So let me just make a note of these. So thyristors. Now the first thyristor that we're going to look at has become a very useful component for us, and it's called the SCR, and this stands for silicon controlled rectifier. Silicon controlled rectifier. And the next component, very, very similar in nature to this, it's actually also an SCR, but it's an LASCR. And so really it's just a silicon controlled rectifier that is light activated. Light activated. And so we'll be looking at that one down towards toward the end of the thyristor group of components. The third is a component called the triac. And you know what's interesting about these three is that these first three are what we call control devices. So in other words, each one of these, you know, in slightly different ways, are used to control the actual load current flowing from a source to a load. And so these three are all in some way controlling, switching, doing something to control the main path of load current. And then because these components actually use a gate, in other words, they operate with an impulse that's applied to a third lead on the component, then we need, if we have control devices, then what we need in addition to that is something to actually control that pulse. And so those we call trigger devices. Trigger devices. And so numbers 4 and 5 are the diac and the UJT. Now the UJT stands for uni junction transistor. And so we will have, for our trigger pulse control, you know, trigger pulse devices that control that small shot of current that goes into the gate of the actual controller, we're going to use diacs and UJTs. And so these we call triggering devices. Trigger devices. Okay, and so that makes up the 5. The SCR, the LASCR, the triac, and then the diac and the UJT. And we'll be talking about each one of these components in turn. And we're going to start with the SCR. So the SCR was introduced, basically became came into use in about 1957. So it's been around for quite a few years. Essentially, it really came into widespread use. More, I guess, it was a little while later before it came into really widespread use. But now SCRs are used for just an enormous amount of applications. And so we're going to go into it. I'm going to explain how this device works. Very interesting. And then we're going to start working with it and doing some circuits and things like that. So just to begin with, let me give you a quick description. This device is one-way current. Okay, so there's no intention for current to go back and forth through this component. It goes one way. So we really say, even though we can use it in AC circuits, it's used as a rectifier in an AC circuit. And so in fact, there's never an intention, and in fact, current never flows back and forth through it. It's always one way, and it's from the anode to the cathode. Now, this actual device has 4 layers, looks like this. Now we start by dividing it up into 4, and on this end, I'm going to put a p-type layer. So this is semiconductor material that's been doped to be p-type. Then we fuse that to an n-type layer, followed by another p-type layer, by another n-type layer. Now, what we learned earlier is that the lead that attaches to the n-type layer should be called the cathode, and in fact it is. The lead that attaches to the p-type material should be the anode. Now, the polarity here, in order to forward bias this, should be positive and negative. Now, on this device, we have one more lead, and it attaches right here, very close. It's on the p-type material, but quite close to the junction of the N. And this lead is called the gate. So we have anode, cathode, and gate. And these, these 4 layers make a very interesting combination. I'm going to explain to you how the current actually gets through here, and how this works in a little bit of detail. But first of all, let me just show you the symbol for this component, and it looks like this. So we start with the anode. Looks a little bit like a diode symbol. In fact, up to this point, it looks exactly like a diode. This is the anode, the cathode, but we have this line, and here we have the gate, and that's how you can tell it. So that's the actual schematic symbol that you would use for an SCR to show it in the circuit. And so the SCR, 4 layers, 3 terminals, anode, cathode, and gate. And the current paths through this device are like this. Our main load current goes like this. Anode to cathode. And when we send a pulse of current into this to actually turn it on, that pulse of current has to come in to the gate, and it flows through and goes to the cathode. So this current, we would say, is I from the gate to the cathode, and this is I anode to cathode. So there are two currents essentially, but just recall that this really is just a quick pulse. So this current doesn't flow all the time. And so very, very interesting the way that works. Let's take a look and see one of the best ways to describe this is by actually using using our explanation of transistors to understand really how this device works. So I'm gonna make a little drawing, and then I'm going to walk you through it, and I'm going to explain it to you. Okay, so I've done a little diagram here. This represents what is going on inside of the SCR. And so I want you to do is take a nice close look. And what you're going to see here is emitter, base, collector. And this is like one transistor, okay, one transistor. And then here you're going to see the collector of this one connected to this base. This is basically another transistor. So I got base, collector, emitter. Now this transistor is like a PNP because this arrow is pointing in. This is like an NPN because the arrow is pointing out. And so let me show you the layers, actually what these layers look like. If we show the material of a transistor, you will see that we have, if we have a PNP, it's like this, PNP. Now, if we were to take this transistor and then take another one and join it together like this, something interesting happens. This one, its layers match up. So this is N, this is P, and then this layer is the N layer. So you can see that we've taken two transistors and joined them really together. And that's what's going on here. This is the anode, this is the cathode, and over here would be the gate. Okay, so this is essentially what we're combining. Two transistor components that are fused together into one component. Now, operation-wise, we need to be very careful and look at this and see what's happening. I want to start with the PNP resistor. Now, we know that the main current path through a transistor is this one, which is essentially going to be E to C. That's the main current path. And that path will only conduct if we have base current here, okay? If we have base current flowing right there. Now, let's say, well, if you look at it, this base current is actually has to go through this circuit right here, and this circuit from C to E cannot conduct unless there's base current here. Now, how do I get base current here? Well, I can't get it from here because this is open, and that's because there's no base current here. And the reason there's no base current here is because it can't go through this contact, and the reason it can't go through there is because I have no base current here. And so you can see that what actually happens is this thing literally cannot turn on. It's locked off, it's latched out. Nothing will go from anode to cathode because these can't start. They can't start till they get a base current, and neither one of them can start as is. So here's what we do. We take a source of voltage and we introduce a pulse of current into the gate. Now this pulse of current enters to the base of this transistor. That takes this switch contact and closes it. When this closes, then current can flow from here through this base lead, because now we've closed this circuit and we're allowing the base current to flow into the collector. Now remember, the only reason this is working now is because we introduced base current here, which closed this contact. This closes, current flows through here into here like this. Now, as soon as current flows through the base here, this contact closes. And that allows current to flow this way into the base here, which keeps this contact C to E closed, which allows this base current to continue to flow, which keeps this contact closed, which continues to pour base current into this base of this transistor. And now the loop is basically, it's latched and it's self-sustaining, and it will continue on in the conducting state from A to K. So very neat the way that works. And this, we call this the two transistor analogy, and it shows very well what is going on in here when you apply voltage and then apply a gate pulse. Now, this component, because it's essentially a component that only conducts in one direction, once you turn it on, as long as you have a supply of voltage, it will just continue to conduct. So let me show it to you like this. If I have this component, and here's my anode, cathode, and my gate, cathode, anode. And let's say this is the load. This is the load that I'm trying to control, okay? So this is a load, it's a DC load. And I have here a source of voltage, okay? It looks like this. Source. Now, as soon as I introduce a pulse of current to this gate, and it only takes a pulse of current that is literally can be measured in microseconds. Microseconds. The range is usually about 30 to 50 microseconds is the amount of time that that pulse needs to be applied for this whole thing to actually close, this to close, and for it to latch on. So as long as you have the right amount of current for between 30 and 50 microseconds, you're good, and away it goes. So once we put a trigger pulse in, now we're going to have current flow through this DC load, through the SCR, and back to the source. And so we're going to be flowing. We're going to use here. We're going to use conventional current flow, and the current will be flowing from positive to negative through the SCR and back to the source. Now, the gate pulse you can see is going to have to be positive with respect to the cathode in order to flow in. So the gate current always has to go this direction. The load current always has to go this direction. Okay, so when the anode is made positive, okay? So as soon as we connect this and we apply voltage, as soon as the anode is positive, and with respect to the cathode, which is negative, what will happen is in the absence of a signal, if there's no gate pulse, then what happens is this SCR will block. Okay, it looks like this. It's like an open switch. Okay, this is when there is no trigger pulse. If there's no trigger pulse, it will block, and it will block to a high level. Depending, we have what we call a forward blocking voltage, and it can be into the hundreds of volts. This could easily be 400, 500, 600 volts here, and this SCR will act like an open switch, and it will easily separate and prevent current flow through the load by blocking all of that source voltage. As soon as we put a pulse to this gate, a trigger pulse to the gate, we are then taking this switch and closing it. And as soon as we close the switch, then the SCR conducts. And as soon as it conducts, the voltage drop across the SCR goes to quite a low level. A to K will usually be in the range of 1.5 to 4 volts, something like that. And it's not an exact number that you can count on. Like when you're looking at a diode and you say, I know the diode is 0.7 of a volt, because there are multiple layers here. This voltage drop is literally because of barrier voltages, but there's several junctions in there, and so it's a little complex inside. So this level varies, and we'll have to look at the actual spec sheets to know exactly what it is. But in any case, as soon as you trigger the gate with a pulse, the switch will close and it will start to conduct. And now you'll only have a small voltage drop across that. We call that the forward voltage. Okay, VF or V forward, sometimes called V on. And it's the voltage drop from A to K when it's conducting. And when it's conducting, then you have a small voltage drop here, and of course, a large voltage drop across the load, because essentially all of the source voltage minus the voltage drop across the SCR. Now, at this point in time, what we have is load current. Okay, load current flowing through the load and through the SCR and back to the negative terminal. So what we're really doing in this instance with a DC supply and a load and an SCR is we are using it as a solid state switch. And as a solid state switch, they're very effective. I'm going to talk a little bit more about that in a couple of moments. But before we talk about the characteristics of the switch, I want to point something out. Once we have current flowing through the SCR, remember that internal circuit between the two transistors is flowing, everything is working. And so there's actually nothing to really turn this off. So in other words, it will continue to conduct indefinitely. So in order to actually get it to open, to turn off, we have to do something. And the term that we use for stopping the SCR, in other words, we want to open A to K, okay? So we can get the current to stop. And the term that we use that is commutating, okay? Commutating. So we're commutating the SCR, and that's actually stopping the SCR. Very similar word to a word from DC machines, but slightly different meaning here, okay? So here, commutating in an SCR means stopping it and getting this contact to open up. Now, in a DC circuit, there's really only one way to do that, and we call it, and I'm just going to add to this, it's called forced commutation, forced. And the reason we say that it's forced is, you know, on its own, it will just continue to conduct. It's all set up. It has everything it needs. So we literally have to get in there and we have to force it to. And so what does it really take for this current that's flowing through here to be stopped? And so what I want to show you is this. This current, I'm going to call the A to K current, okay? It's the current that goes, first of all, through the load, and then from A to K. Now, this current could be as low as a couple of amps or even less, but it could also be as high as 4,000 or 5,000 amps. And so regardless of the amount of current, you know, larger currents are going to mean it's going to be a much larger, higher rated SCR. But either way, there's one value that we have to know about, and it's called I of H. What this stands for is holding current. So every SCR has a rated holding current. And let me just give you, I'll give you an example that looks like this. Let's say that I have an SCR here, and here's my A, and here's my K. Okay, there's the gate. And the maximum current, which I'm going to call IT, that's the total forward current. Let's say that it's 2 amps. Let's say it's rated for 2 amps. Now, just to put that into a different terms, that's essentially 2,000 milliamps, right? So 2,000 milliamps is the actual load current. What happens is, if I start to slowly reduce this current, and one way that we could do that would be if we could vary the voltage of the source and we could vary it down. What would happen is this current would get lower and lower. It'd go 2,000 milliamps. Finally, it would get down to 1,000 milliamps. Okay, it's going down. Finally, it would get down to 500, probably 250, then maybe down to 100. At some point, we're going to reach a current level, and that current, that holding current, is the amount of current that has to be going from A to K that will satisfy both bases and keep everything latched in. And I'm going to say, just for an example, that this one is 75 milliamps. So when we get down to 75 milliamps, the current all of a sudden goes like this. It's going down, right? Down, down, As soon as we get to 75 milliamps, all of a sudden, bang, it goes straight to 0 milliamps. So the SCR shuts off, the junction opens, and the current stops. So if we were watching the current, it would come like this. If we said this is 2000 milliamps, and I'm just going to graph it. We said it was coming down like this, like this, like this, like this. All of a sudden, when we got to, if this was 75 milliamps right here, all of a sudden the current would go like this. So if you were to graph it, it says it doesn't continue on this line. This point is where we reach our holding current level. Bang, it just shuts off, immediately goes to 0, okay? So holding current is going to be a very important feature of this for us, and just understanding that it's actually the A to K current. When it gets down to this value, it will no longer actually hold in the circuit. Now, DC equipment, so the equipment, switches, contactors required to handle DC loads, turn them on, turn them off, have always been very large size, and that's because DC current is not easy to interrupt. And so I've actually drawn here on the board, this would be a mechanical, about a 40 amp DC switch. And I've actually drawn it pretty close to its actual size, believe it or not. So a couple of hands high, a good hand and a bit wide, and probably 4 to 6 inches deep. And that switch would be rated for about 40 amps. Now what you would have inside would be an actual jaw, a spring-loaded jaw, and then you'd have the actual arm of the switch. Okay, this blade would basically pull out. So you'd be a handle on the side. When you pull this down, the handle would go through like this essentially. It would be keyed and come through here, and then you would have it coming like this, right? Now, when you pull down on this handle, this blade pulls out, and then you would interrupt your current. Now, one of the problems with DC current when you try to break it is that as you open this, as the blade basically leaves the jaw, very often there will be an arc drawn. An arc is a little bit like welding in some ways, so it can create spits and little tiny bits of particles of molten metal, and it roughens up and it raises the resistance of this. So there's lots of maintenance involved with DC switches, plus just their actual physical size is very large. That's about a 40 amp mechanical switch. Now, as a switch, an SCR does a lot of things really amazing. And let me show you what they are. Essentially, with an SCR, there are no moving parts. Okay, no moving parts. So all of this stuff, if you've ever worked on any of these, these handles, there's bushings, there's pins, there's all sorts of things. If they get a little loose, they jam. There's a whole bunch of mechanical things to take care of on this type of switch. So with an SCR, no moving parts. An SCR, no arcing. Okay, so when an SCR shuts off, it just shuts off, current stops. Here, when you pull this out, you get arcing at the contacts. No pitting. So pitting is the actual, it's when the arc draws out and it leaves little weld marks or little holes, little spit marks there. That's called pitting. SCR does not suffer from that. A mechanical switch like this, depending on its environment, can definitely be degraded by corrosion. Okay, so you can get rust, you can get patina, you can get dirt into it, dust, grease, any of a number of contaminants, generally speaking, that can gum it up. Now with this, no corrosion, and essentially no real grime builds up in it. Okay, so really they stay quite clean. Everything is internal inside of that semiconductor material. And another thing that happens, not so much with these switches, but when you have contactors, where you have a mechanical contactor, a magnetic contactor that is closing and opening, those ones, when the spring hits, they would actually sometimes cause a contact bounce. And that bounce creates an arc. And this is one of the things that we say about the SCR is that there's no contact bounce. So it's just a firm, positive, the current starts, the current stops. Absolutely none of the issues really that happen with this switch will happen with the SCR as a switch. Now, I want to show you something really kind of remarkable. This is drawn actually pretty close to actual size. And this is a 40 amp switch. And I want to show you a 40 amp SCR. And you can see actually, this is the SCR right here. And you can scale it to size. This is just a, this is just a flash drive that I had in my pocket, just so you can kind of see the scale. That is a 40 amp SCR. And so it is totally capable of making and breaking the same current that this physically sized switch would be able to make and break. So the SCR as a solid state switch does a remarkable job. So let me summarize. The SCR then. Here we have a switch. It's a current controlled switch. Okay, and it's a gate pulse that basically operates it. Gate pulse. And once you do that, it latches. So it takes no further current to hold it in the conducting state. What we need to do, so this is basically on, we need a gate pulse. Off, well, we have to force it off. Forced commutation. And the way that we have to do that is we have to reduce the A to K current below the holding current value. Holding current value. And that's I of H, okay? So the way to shut it off is to force it to shut off by reducing the current below that level. Now, I just want to restate the current for these, the typical A to K current through the SCR, A to K, there's your main current path, anode, cathode, there's your gate over there. This current is basically ranges between about 1/4 of an amp to around and over, sometimes over 5,000 amps, okay? So lots and lots of current. Now, obviously, these are going to be enormous once they get up into the thousands of amps, but it's pretty impressive to see how small even a 40 amp SCR actually is. So when it comes to the specifications of SCRs, there are several important ones. There are a lot more than what we have here, but these are the main ones I want to cover just so we can understand what some of the key things are that we need to be aware of when we choose an SCR. And so let me start here with the first one on the list. This is IT RMS, I total RMS. Now, I just finished saying to you that the SCR is actually always has current flowing in one direction, so kind of DC, right? But let me explain it like this. You can have an SCR that is in a circuit that has been rectified that has waveforms like this that are appearing between its anode and cathode. And that means that really this waveform voltage because the voltage will actually be down here somewhere, but you have these peaks that are being expressed across it, it's going to change the value of current that this can handle. And if we look at I average, that's just straight up like a DC voltage. That's like this. This is like straight line DC voltage. You know, here's 0 volts and here's whatever this is, say 50 volts. So basically DC voltage average, RMS is where we're being fed from waveforms like that. Now, so this total is the A to K current. That's the main load current that we can handle. Now, in this little guy that I just showed you, 40 amps. Okay, 40 amps for that one. So, um, so the rating will be slightly different depending. This is also just depends on how the DC is made, whether it's from a filtered DC source or whether it's from a rippling rectified waveform source. Now, the amount of gate current, so the amount of pulse current that has to go in order to successfully turn the SCR on is called IGT, or gate current. Usually this is measured in milliamps, okay? And in some applications even less. IGM, what that is the maximum gate current. Now, this will make a lot more sense a little bit later on, but even though this gate current may be in the milliamps, this can be rated as high as between 2 to 5 amps, because sometimes, depending on the firing angle, you could have a very small current, but its maximum at some point in the waveform that's feeding that pulse current in, maybe it's going to be a little higher. So we do have a maximum current rating for the gate. Still quite a low value when compared to, say, the 40 amps from A to K. Now, I holding. This is the required A to K current to maintain conduction. Okay, so we have to have at least that much current, or there's not enough current to satisfy what's going on inside that two transistor analogy, and it shuts off. So holding current, a level of current that we must have in order to maintain conduction. Now, VDRM. Now these voltage ratings are all essentially quite interesting. The first two are blocking voltages. In other words, these are the ability of this device to actually remain open and block voltage. The first one is in the forward direction. In other words, if we do not give a gate pulse, this will block in the forward direction, forward blocking, and it will not conduct. Now, if you were to take this, now we know that current only goes in one direction. Well, what happens if you reverse bias the A to K junction? You make K positive and you make A negative. Is there any way it will conduct? And the answer to that is no. It has a very high blocking voltage. We call this the reverse blocking. Okay, reverse blocking. And it always blocks. The only time that it doesn't would mean that it had failed. Okay, so it definitely reverse blocks. These two voltages are usually quite similar. They for this SCR here, for this one here, bring it closer. The blocking voltage for this SCR is about 600 volts in each direction. Actually, I think it's about 700 in the reverse blocking direction. Now, voltage F, and I'm going to say this could also say on, so voltage forward or voltage on. This talks about the voltage drop that you'll see from the anode to the cathode during its normal operation. So this is really voltage drop A to K during conduction. Now remember, this SCR is actually like a switch. And so when it's closed, our idea with switches is when a switch is closed, there should be no voltage drop across it. We don't want we don't want a switch to be a resistive device that's creating heat in a circuit. But it is one of the things that we have to sacrifice for having all of the other advantages of the SCR is they do drop a little bit of voltage and they have a little bit of power loss because they get warm a little bit when they're conducting. So one of the small inefficiencies, but yes, there will be that forward voltage drop. Now, just one voltage drop left, very important one, and this is VGT. Now, the voltage that the gate drops as the pulse is going in. So we know as current flows through a device, there's going to be a voltage drop. Now, if it's a semiconductor, like a diode, just a silicon diode, it's typically 0.7 of a volt. Now this one, even though it's going, it seems like it's going just from the P layer to the N layer. It's a little complicated because there's actually two P layers connected together in there. And so the voltage is typically more than 0.7. Usually it can be 1.5 to 2.5, 3 volts, sometimes maybe even 4 volts on really large SCRs. So this VGT is the barrier voltage drop on the gate to cathode. Barrier voltage drop, gate to cathode. And now this also has a reverse voltage rating. And what happens is it's a very small amount of voltage, usually only about 5 volts. The gate is never intended to actually handle reverse current. And so typically what happens if there's any mistake in the circuit and any voltage is applied in reverse on the gate, or you get any current sort of flowing backwards through the gate, typically it just blows the gate up. And so the gate current really needs to go from the gate to the cathode. And this would be the amount of voltage drop. And this would be actually part of the trigger circuit. Because remember, that is the trigger pulse going into the gate that's going to turn this SCR actually on, okay? The waveforms that appear across the SCR and the load are something that we need to be familiar with to know what they look like. So what I want to do, I'm going to show you a circuit, just a small circuit, and it's going to look like this. Positive source, load, and the switch. This is going to be the anode, the cathode, and the gate. And this is going to be negative. Okay, so there's my potential, positive to negative, and that's all there is in this circuit, okay? We want this to act as a switch to turn this load on and off. What I'm going to do, I really want to see what's going to happen. So I'm going to put one scope lead here on this point, and then I'm going to take this and attach it to here. And this channel, I'll call this channel A, is going to look at what the waveform looks like on the load. Then I'm going to put channel B right here. And the interesting thing is that, in the lab, this is something that you need to pay careful attention to, and you'll notice it as I'm doing the lab experiments. When I use 2 channels, you only use 1 ground. So in other words, this lead will show me something on the scope with reference through this SCR to this lead right here, which is on this point. And this channel will show me what's on this load up to this lead. So the common lead is in the middle. If you use a second ground lead on this, then you create a short circuit and it'll actually blow the fuse in their power supply. So one channel here, this is going to be channel B, okay? So channel B. And what I'm going to do is I'm going to draw the waveforms for you, and it's important that we can see what these look like. So let me just put a little graph here. This would be like a little scope window that you would see. Okay, so this is going to be channel B over here, which is going to be the SCR, and this is going to be the load. Okay, and I'm going to say that this voltage is 20 volts, 20 volts, and I'm going to say that the VF of this SCR is 1.5 volts. Okay, so the VF is 1.5 volts, and then I'm going to show a line here. This represents 20 volts, 20 volts, and 0 volts down here. And this represents 20 volts and 0 volts down here. Now, if I apply power to this circuit, what's going to happen is, to begin with, the load will actually have 0 volts. So I'm going to show it like this. Now, why does the load have 0 volts to begin with? And the reason is that as soon as I supply voltage to this circuit, this is an open switch. And remember, from your two transistor analogy, there's no way that one transistor can turn the other transistor on until we receive a gate pulse. And until that happens, this is going to look like an open switch. And so what will happen is that the load will have no voltage, and the SCR, being an open switch, will show 20 volts across it. Okay, so during the same period of time that the load has 0 volts, the actual switch, or the SCR, will show 20 volts. Now, what happens next? Well, we come along, and at this point, this is where I fire the SCR, and that's a term that we use to represent giving it a trigger pulse. We call it firing the SCR. So we fire the SCR at that instant in time. Now, what happens is the SCR voltage, what you'll see on the scope is that this line will go straight down, but it will not go all the way to 0, because this 1.5 volts will actually show up on the scope. So you'll see a line like this. So this voltage will move across in this way. Now, what happens to the load at the same point in time? Well, the load will turn on, but seeing as the load is in series with the SCR, and you have 1.5 volts here, we know that the total voltage drop across this circuit has to equal 20 volts. So that means that this will be 18.5 volts. So once we have triggered the gate, this will be 18.5 volts. And so this will move across like this, just a little bit below that 20 volt level. So our load doesn't have quite 20 volts, it's just a little bit less. And our SCR isn't quite at 0 because it has that 1.5 volts drop across it. Okay, now, remember, this is going to continue indefinitely unless we force it to actually shut off. And so what we'll do is we'll commutate the SCR, and when we do that, the load voltage drops straight back down to 0, and it will just stay at 0 as time goes by. And what will happen to the SCR is it will go back up to blocking the full 20 volts, and it will move on in time that way. So this is what the two waveforms will look like. I say waveform, there's not much of a wave to that. It's really just a square tooth that we're looking at. Now remember, this is a filtered, direct, pure DC, straight line DC. And so this is what you would actually see in terms of if you put the scope on when you're using it as a DC switch. All right, so I'm gonna just, I'm gonna summarize then. We've been looking at the SCR, and the very first application is using the SCR with a DC power supply, and we're using it as a solid state switch. And you know, we've looked at the advantages of the solid state switch, we've looked at the waveforms, and we've gotten that basic understanding of how the actual SCR operates. It's a fascinating component, and it really acts exactly the same as a latching relay. Back in the day, we used mechanical relays that were latching relays, and this performs very similar in a very similar way. So the next thing we're going to be doing is we're going to be seeing how we can actually use this as the way that it's named, which is as a rectifier. So we'll be taking this SCR, hooking it up in AC, and we go, wait a minute, it's a DC component. Yes, that's true, but it's going to be like a diode. It's going to give us a DC output, but it's going to be controllable, unlike a diode. And so we're going to now be able to take either the whole alternation or just a piece of the alternation. And so that's what's coming up next. And so that will be probably tomorrow. We're going to start on that. And so stay in touch, and we'll be looking at that soon.